All right, so folks, we're moving on to a new chapter. We're actually going to skip chapter 7 for now. We're going to come back to it after we do chapter 8. We are moving on to chapter 8, and the star of chapter 8 is trigonometry. All right, trigonometry. Trigonometry. I don't know about you, but like, there's a few math words that like I feel like. You know, on a TV show or something, when they're trying to sound nerdy, like, or trying to make someone sound nerdy, they'll bring out a few words. Like this person will say, like, "Oh, I love algebra." Like they'll use the word algebra or trigonometry. I find trigonometry like, "Oh, trigonometry is the best." Like I feel like it's one of those words that they throw out to make someone sound nerdy. Trigonometry is actually kind of interesting. I think a lot of people like trigonometry because it's pretty different from other math that we're doing. Trigonometry is kind of like an area of geometry, so like with shapes and analyzing like angles and area, that kind of thing. Okay. The word trigonometry has, trying to get my annotations out, has this tri prefix to it. So it makes us think of 3, right? Or triangles. So trigonometry does have a lot to do with triangles. In fact, what we're going to focus on in Math 10 is right triangles. Okay, what is a right triangle? Somebody please tell me, what is a right triangle?
Triangle. I don't actually know.
Don't know? Okay, I thought I heard someone in that room with you, Ruben, say c squared.
Oh yeah, my dad. Yeah, we were talking about a squared plus b squared equals c squared.
Why were you talking about that?
Because my dad's a construction worker, and I was saying that we're getting into trigonometry, and he says to square off corners, they use Pythagoras' theorem of 3, 4, 5.
Yeah, I've heard that before. That the Pythagorean theorem, which you may remember, is a squared plus b squared equals c squared. It's a relationship between the sides of a right triangle, right? And one of the nicest, one of the kindest is this one here, right? This, if you draw a right triangle and one of the arms is 3, the other is 4, we know for sure that this last one is going to be 5. Usually with a right triangle, like for example, if I had 3 and 6, this last one is going to be some weird decimal number. Like it might be 7.125 something, right? But there are a few very kind right triangles that are nice even numbers like this one. All right, so this is a right triangle here. A right triangle has one angle that is 90 degrees, okay? So when we use right in mathematics, we're usually referring to a 90-degree angle. So this triangle has a 90-degree angle. Someone else drew one here. Thank you, TY. TY for thank you. Okay. So we're going to learn about these 3 things: sine, cosine, and tangent. All right. We're going to learn how to use them. The rest of the chapter really is based on those 3. We call them 3 ratios, 3 trigonometric ratios. Okay. Say that word or those 2 words 7 times fast. Trigonometric ratios, trigonometric ratios, trigonometric ratios. And so you can see that we're kind of basing everything off of those. So we're going to be dealing a lot with trigonometric ratios, and so there's a few terms that we should be familiar with. First of all, I want you to look at this little guy in the corner. Do you see this guy? See that guy? You seen him before? You seen that guy before? If you lived in ancient Greece, you may have seen this on signs.
I have family that lives there, so I mean, I've never seen it, but in ancient Greece, no, I'm kidding.
No, in ancient Greece, yeah. So we've got, this is a Greek letter, and this Greek letter is theta, okay? So you should remember that, theta, not like the cheese, theta, cheese, theta, cheese, okay? No, sorry, it's theta, the Greek letter. And this Greek letter, you know, we could call an angle X or Y, but we usually, almost always, call these angles theta. That's kind of the most common. So this symbol is just like X or Y. You know, it's a variable that is unknown, and it's usually given to an angle. You may also see other Greek letters like alpha and beta. All right. Now this angle here, let's say he's the star of the show, right? It's his birthday party. We'll give him a birthday hat. There we go. Okay. It's his birthday party. He's the star of the show. What we do with these right triangles, and this is a right triangle. Look at that nice right angle right there. What we do with these right triangles is we name the sides in relation to that angle. Okay, to some angle. We name the sides in relation to that angle. Let's start with this one, right? This side here has a special name. It's the one across from the 90-degree angle. Do you remember what it is? You may have learned it when you learned about Pythagorean theorem. It starts with an H. No.
Hypotenuse.
Yes. Hypotenuse. It's kind of hard to spell. Okay, but there it is. Okay, hypotenuse. So it's always across from the right angle. Anything else interesting about the hypotenuse? Something that's true about all hypotenuses.
The longest side of the triangle.
Exactly. They are always the longest side of the triangle. Excellent. Good. So we have the hypotenuse. So that one is always that one. If you imagine our star of the show, theta, having to walk across a triangle, he would get to this, this opposite side, and that's what we call this one. We call this one opposite. Okay, this is the opposite side. Okay. And then if you imagine this theta could kind of reach out his hand and touch this one, he's right next to it. And so this one is next to or adjacent. Okay, so we give it the name adjacent. All right, so we have these three sides of a triangle: hypotenuse, opposite, and adjacent. Okay, clear? Clear so far? If it was no longer that guy's birthday, if instead it was Alpha's birthday here, okay, I'm trying to make it a fancy A, it didn't really work. If it was Alpha's birthday over here, the hypotenuse is always a hypotenuse. But now, like now if we're focusing on this angle here, our new opposite is over here, and our new adjacent is over here. Okay, so just a reminder that it has everything to do with the angle in question, the star of the show. All right. Questions so far? Okay, great. All right. Do you guys have a scientific calculator with this button on it? I don't know, maybe. You might. Have you ever wondered what this button does? Or maybe you've tried like pressing it and it just like, you don't know what it does. This, we've talked about functions before, and very commonly we have a function called f, and f of x does something. It relates x, the input, to y, its output. So this could be like x squared. Well, tangent here is a function, and so we often actually see it written out like this. We'll say tangent of some input, and then it will spit it out, right? So just like this one, f of x, if I plug in a value f of 2, I know that I'm going to get an output of 4. Just like that, I can plug in a tangent of 0.5, and I'll get, this one should be easy, I think. I'll get some random number, right? Well, seemingly random. It's a number that is useful to us. All right, so it's a function. You plug a number into that function and it will spit another number out. Okay, so you put one number in, it's like a machine. You put one number in, it spits another number out. It is not random, right? In fact, before people had those buttons on their calculator, textbooks would include big tables like this in their textbook. And so if we wanted to find tangent of 15, what you would do, oh, actually we said tangent 50 before, right? So let's see what it actually is. I thought it was something nice. If we wanted to find tangent 50, what you do is you find the angle. Here it is, tangent 50, right? And yeah, it's degrees. We're going over to tangent. Here it is. Tangent 50 equals approximately 1.192, right? Or if you want to, you can use a scientific calculator. I really like the Desmos scientific calculator here. You got to make sure that you're in degree mode. See that? We're in degree mode. And we can go tangent 50. We get, yeah, about 1.191. And then there's some more decimal values there. Okay. So far, we're just getting used to the idea that tangent is a function. I can plug in a number and it will spit out another number. If I get tangent 20, it'll spit out this 0.3639, right? Or 3640. Just like, hey, if I use this chart and I went tangent 20, I would like to clear. I found tangent 20. Here it is. That's my angle. Here's tangent, 0.364. 0.364, and we saw that it would round to 0 there. All right. Okay, questions so far? These numbers serve a purpose. These numbers help us do things with triangles. We're going to get to that. Okay, we're going to get to that. Those numbers help us do something with triangles. What we will do right now, though, we will set a timer for 8 minutes, and we'll see you after the break.
You have no idea how hard this is to do with a touchpad. For that from Mr. Moore, we can understand you can draw good circles with your pen thing.
That makes so much sense. I always suspected that Mr. Moore had one of those, and I was like, I never knew, because I just use my mouse on my keyboard.
Yeah, I have a touchpad. I don't even have a mouse.
Yeah, I have a touchpad too, but
it's tough with a mouse.
Yeah, and a trackpad.
Yeah.
What's your name? I don't think I can actually write. I'm not even gonna try.
All right, here we are, folks, making interactive comic books. This is a story of when I don't know what is that thing? It looks like a little gremlin or a goblin or something.
Then it's a little gremlin or goblin or something.
Okay. Meeting a blob, and the blob is kindly saying, "What's your name?" All right.
Is it a blob king?
Yeah, that's
yeah, it's king of the blobs. Yeah, yeah. All right. So, folks, we talked about tangents. And in addition to tangent, all right, first we got to say goodbye. Goodbye. In addition to tangent, there are the two other trigonometric ratios that, you know, if we had these tables, we would have to use these for them. We have sine and cosine, sine and cosine. So very often these are written as functions like this. Sine looks like sin, and then we'll have our input, which is usually theta. Cosine is cos, where we will have our input theta, and tangent is tan. We'll have our input theta. So this tells us, because the inputs are these thetas here, what does theta usually represent? What type of measurement?
Angle.
Angle, yeah. So these, and we can kind of see a hint to this here as well, these functions usually take an angle as an input. So we'll plug an angle into there and it spits out this other decimal number, this weird decimal number that we're going to talk about soon. All right. I want to talk about triangles. What are the same about these two triangles?
They have all the same angles.
Oh, they appear to, and yeah, that was intentional, that all the angles are the same. So of course we have a right angle here. We can call this angle A. We should use capitals actually. Angle A is equal to angle A over here. Angle B is equal to angle B over here. All right, great. Anything else that's the same between these two? I'm surprised no one has said color. The color of these two triangles is the same. All right, so yeah, color is the same. Now, there is something else that's the same between these two triangles, right? So the angles are the same, excellent. There's also some sort of ratio between the sides that is the same. So let's say that this big triangle has a length here of 10, and then maybe the length here is 8, all right? Okay, so we have a length of 10 and a length of 8. If this smaller one over here had a length of 5, could you tell me what the length here is?
4.
Yeah, yeah. There's some sort of ratio between the lengths of the triangle. This reminds us of learning about similar triangles in previous years of school. Similar triangles, similar shapes, right? That have the same ratio. And so this becomes very important. Okay. This also gives us a hint that, hey, if I know an angle and one side, I should be able to figure out what the other side is. Give us a little bit of a hint there. So let's see this kind of in action. Let's say that we've got these two triangles here. What's the same about these triangles? Well, they have the same ratios. Okay, they have the same angles. They have the same ratios as well. So the ratio of the side lengths of the small triangle can be written as opposite over adjacent, right? So here's our star of the show, right? That theta there. Opposite over adjacent, right? So let's see what that is. What is the side length opposite to this theta? What's the side length opposite to theta here? What is the number that is its side length?
4.
4, yeah. Opposite, remember, we have to walk across a triangle. So that's 4. And how about adjacent?
3.
3, okay. So we've got a ratio here that is 4 over 3. This is opposite to adjacent. Okay, the ratio of the side length of the large triangle, well, let's do that as well. That's, you know, opposite over adjacent as well, right? We're just picking these two side lengths, okay? And this is 12 over 9, right? Opposite is 12, adjacent is 9. However, this can be simplified. how can I simplify this fraction? How can I simplify it? Or what can it simplify to?
Divide it by 3.
Yeah, divide the top and the bottom by 3, and I end up with 4 over 3. The same ratio that we had over here, right? So if theta is the same, right? If this theta is the same, then the ratio here is going to be the same as well. Okay, so if this angle is the same here and here, okay, this one and this one, if they're the same angle, then these ratios are going to be the same as well. Maybe the sides are bigger or smaller, but the ratio stays the same. So, since the angles in the side length ratios match on similar triangles, we can count on a special relationship. Those relationships are the trigonometric ratios. Okay, so we're beginning to see that, okay, there's some consistency. There's some really, really nice consistency with right triangles. They're very predictable and they follow a certain pattern. And this means that we can rely on these trigonometric ratios. All right. So the tangent ratio, it is a ratio, so one number over another. The tangent ratio is defined as opposite over adjacent. Okay? Opposite over adjacent. So this lets us find a missing side length when we know an angle. So let's say that we didn't know this side length. Let's say we didn't know, yeah, sure, this one, okay? And let's say that we knew that this angle here was 50 degrees, okay? We're bringing back that 50, okay? We can do some work to find out what this side length is. I know it was 9 before, but I'm making up a new triangle, okay? This is a brand new triangle, so the answer is not gonna be 9. We can figure out what that side length is going to be. And what we do is we always start by writing out the general form here. This is what I always do. Okay, pay attention. We're going tangent theta equals, I usually write it like this, op over adj. Okay, opposite over adjacent. That's the tangent ratio. And then let's plug in the info that we know. So do we know the angle? Yep, we know that the angle is 50, so I'm going to plug it in there. Excuse me. Do we know the opposite? Yes, the opposite is 12. Do we know the adjacent? No, maybe I'll call that x, right? So we want to try to isolate that x value, and kind of the nicest, there's this really nice shortcut you can do. You know, we are going to think about doing this. We multiply both sides by x. We end up with x times tangent 50 equals 12. Okay. And then now we can divide both sides by tangent 50. So we end up with x equals 12 divided by tangent 50. Okay. X divided by tangent 50. Depending on your calculator, you might have to do this in a different order. But what we can do now, folks, we can open up our scientific calculator here. We're going to go, we have to go 12 divided by tangent 50. 50, there we go. And we get this number, 10.07, okay? About 10.07. 10.07. And that tells us that the length here, sorry, backing up, that the length of this side, we found it, is 10.07. All right. So what we did is we just used a side length and an angle to find another side length. Use a side length and an angle to find another side length. Something you have never done before. maybe. There's also something we call the inverse tangent, or sometimes called the arctan function. Okay, so it always has this -1 here, and this tells you that it's kind of the opposite function. So it does the opposite thing. This lets us find an angle when we know two sides. So we'll look. Sure, we'll look at this example here, and then we'll check out some others. So we've got a surveyor. He wants to determine the width of a river for a proposed bridge. The distance from the surveyor to the proposed bridge site is 400 meters. We can see that here. The surveyor.
That more looks like a Moses thing going on, like a wall of water just going on right now.
A wall of water. Yeah, it looks kind of like it's going straight up. It's supposed to be representing like looking top down. The surveyor uses theodolite, maybe that's how you pronounce that, to measure angles. The surveyor measures a 31-degree angle to the bridge site across a river. So he's able to build this right triangle shape. And this is a fairly realistic application. I mean, you could get a rope and swim across a river and measure that rope, right? But this way you stay dry. The question is, what is the width of the river to the nearest meter? Well, first of all, what we do is we double check that we have what sides we are using. So I'm going to label these. This is our hypotenuse. Hype is our opposite, op, and this is our adjacent, right? In reference to this 31-degree angle. Then I start, I'm using my tangent ratio because I see that we have opposite and adjacent. These are the two. I can ignore the hypotenuse. I'm not given any information about it, and I'm not asked to find it. So opposite and adjacent, that tells us we're going to use tangent. And so I write out my blank form like so, opposite over adjacent. And then I fill in the information that I do know. So in this case, I know my angle is 31 degrees. I know my opposite. Actually, no, sorry, I don't know my opposite. Maybe I give it the variable x. And I know that the adjacent is 400. Okay, this is nice. All I have to do is kind of move that 400. So I multiply by 400 there and there, because it cancels out there. And then we get this equation, 400 times tangent 31 equals x. So let's do that calculation. Try it on your own, folks. Get out your calculator, okay? Get out your calculator and just make sure that you know how these calculations, like how your calculator understands them, because sometimes on your calculator you have to do tangent 31 first. I feel like I searched for a scientific calculator earlier. I think it was this one. Okay, so you might have a calculator that looks something like this. And so what you might have to do is you might have to first type in 31, and then you hit that tangent button. It gives you a decimal number, and then you can multiply that by 400. Okay, and we get an answer of 240 about. But folks, I want you to do it because you might get something very different. Please let me know if you get something very different. Notice that your calculator, most of your calculators, you'll be able to switch between two modes, degree or radian. Degree or radian. You want to be in degree mode. You won't go into radian mode until pre-calculus 12, okay? So degree mode. If you're in radian mode, you're going to have a bad time. You're going to get the wrong answers, all right? Did you guys get this number, 240? folks, I do want you to try it. Let me know if you get something else. You're probably just in the wrong mode, but this is going to be like, we're going to do this so many times in the next chapter. You got to know how to do beats.
I got 240.
Great, good. So we figured out that the river is 240 meters wide. That's actually a pretty big river.
That's a substantial river.
Yes, that is. All right, in your textbook, you can read a little bit about trigonometry. This diagram here is trying to illustrate how this, a different ratio now, opposite over hypotenuse, remains consistent, right? If we imagine that we have 1, 2, 3, 4 of these triangles, each one getting bigger and bigger. If we have a 30-degree angle that's common with all of them, the ratios stay the same. So this first one has a ratio of 1 over 2. 1 over 2. The second one is 2 over 4. Yeah, it's trying to say 4 there. Okay, 2 over 4. But that, of course, simplifies to 1 over 2. Or, 0.5. These both are 0.5. And so on, right? All of these will have the same ratio. So again, we're trying to show that, that the ratio is consistent. Okay. So we learned about the tangent ratio already. We're saying that tangent is opposite over adjacent. But we have two other ratios, and this accounts for all of our sides and all of our relationships. We have cosine, which is adjacent over hypotenuse, and sine, which is opposite over hypotenuse. So we have our three ratios here: sine, cosine, and tangent. And it can be maybe a little tricky to remember all of these. So folks, are you familiar with this? Have you seen this before? Maybe written somewhere? SOHCAHTOA. SOHCAHTOA. It's kind of a silly made-up name, but SOHCAHTOA helps us remember our three ratios, because the SOH tells us that sine is opposite over hypotenuse. Okay, and then the CAH tells us that cosine is adjacent over hypotenuse. And then TOA tells us that tangent is opposite over adjacent. Okay, so it's a mnemonic, right? It helps us remember sine, cosine, and tangent. All right, we're going to look at a couple of examples. Example 1, very straightforward, just asking, use a calculator to write the ratio in decimal form. Okay, so it's just asking us to practice using our calculator. So we see our answer there, but let's try it. You're going to put into your calculator sine 65, okay, sine 65. So you can use a calculator like this. And we can type in there sine 65, you get 0.9063. Or maybe you're using a calculator more like this. We want to clear out, and we might go 65 and then click sine. And it gives us our number there. If I was in a campus school at this point, what I would do is I would go around the classroom and I would check everyone's calculator. So folks, what I want you to do right now is to have this number on your calculator and hold it up to your screen, to your camera, right? I want to be able to see this.
I don't have a scientific calculator, so I just did mine on Desmos.
Good. You did yours on Desmos, okay?
Yeah.
You don't have
a digital calculator as well.
Okay.
Yeah, me too.
All right. So folks, you don't have a handheld calculator?
Not anywhere nearby that I could possibly find.
I see. Okay. All right. If you have one in a digital one, okay, I understand. I can make you screen share, but I'm not going to go and do that. Okay, but please do make sure that you're practicing using these ratios. All right. So there we go. That's that. Given the decimal value for the trigonometric ratio, solve for theta to one place. So we learned about theta is often or always the input, right? But we have something that reverses the input and output. It's the inverse tangent. So when we're given a ratio, we need to, in order to find the angle, right, the angle will equal the inverse tangent of our ratio. So let's try 2a here. 2a, we're doing sine. Okay. In order to find that theta, we use the inverse sine on the ratio. Okay. So let's try it. There we go. Theta equals the inverse sine of 0.6358. Okay. So I'm going to put that down here. And on our Desmos calculator, you might not see it right away, but what you may need to do is go to function. You do inverse sine, and then you go 0.6358. And we get an angle of about 39.5. This tells us that if we have that ratio, we are getting an angle out about 39.5. On your calculator here, like this, you might have to type in a 0.6358. And then you might have to, on your calculator, you might have to press shift sign. You might see it as like a highlighted thing, so you might have to press shift sign. On here, we can just go inverse sine, and we get 39.5. Right, like if you have a calculator that looks something like this, see how the tangent button is there, and above it is the inverse tan to the -1. So you have to find your shift button and then press that to do inverse. All right. Good. So there's your answer. Theta equals the inverse sine of those things. All right. We also often have questions like this where we're asked to solve a triangle. And when we're asked to solve a triangle, we're asked to find all the missing angles and side lengths. Okay. All we're given is one angle, one side length. Let's do it. First of all, let's tackle y here. Okay. Y is involved with, if we look at y, that's our opposite, this is our adjacent, and this is our hypotenuse. Okay. So we want to involve a ratio with opposite and hypotenuse. Which ratio is that? Which ratio? Sine, cosine, or tangent?
Cosine.
Cosine would be for the adjacent one here. Remember, so toa.
Right. So it is sine.
So it is sine, yeah. We're going to do sine theta equals opposite over hypotenuse. Okay. I fill in the info that I do know. I know my angle is 35. Sine 35 equals y is my unknown over a hypotenuse of 12. So then y equals 12 times sine 35. Open up our calculator. 12 times sine 35 equals about 6.88, let's say, or 6.9. I think we're okay to round to that value. So we found one of our side lengths, 6.9. 6.9. To find our last one, we have a couple of options. We can actually use Pythagorean theorem if you feel like it. Or we now realize that, hey, now I've got, now I can use the cosine ratio to do adjacent over hypotenuse. Cosine 35 equals x over 12. And it looks very similar. We get used to certain patterns with trigonometry. We're going to do 12 times cosine 35. In fact, I'm just going to backspace and change this to cosine, and we get 9.8 about. Okay, so our x value here, x value is about 9.8. Okay, 9.8. All right. We have to find our angle here too. Angle, we can use a ratio again, right? We can kind of let this be the star of the show. Now we know all these side lengths. We can use any of our ratios, our inverse ratio, like inverse tangent. So let's try that, actually. Let's try, we won't use tangent, but let's try sine. Inverse sine. So we're finding alpha, that's the inverse sine of, and here our ratio, right, is what we're putting in there. Our opposite from there is 9.8 approximately over the hypotenuse, which is 12. So that'll tell us what the angle is. So we're going to go the inverse sine. Inverse sine of 9.8 divided by 12. We get about 54.7, about 55 degrees. We're saying that our alpha here is about 55 degrees. All right. Okay. There's another way to find angle. Of course, if we know that this is 90 and this is 35, okay? How many degrees? If we add up all the angles in a triangle, what do they add up to? They add up to 180, okay? They add up to 180. If you add up all the triangles, all the angles in a triangle, they would add up to 180. So we could go 180 minus 35 minus, of course, we got a 90-degree angle there. That will equal 55 degrees. All right. Folks, do you see what time it is? It's 10:22. As you can see, I did come up with a homework assignment. All right, if you want to get a head start, you can work on this. This is going to be joined up with next class's homework assignment. Maybe I'll take out like question 4 or something like that, or I'll take out a couple. I don't want to give you homework. Instead, I want you to just kind of really like, oh, you got like a couple of days to just really think about trigonometric ratios, and you can just kind of mull them over in your brain, you know, like, yeah. Also, plus you got that quiz that's going to open up later on today, so you can study, you can work towards that. No homework unless you want a head start. That's it for today's class. All right. We'll see you again on Wednesday or Thursday. All right. So you are officially dismissed.
Thank you.
You're welcome. See you, folks.
Thank you, Mr. Bohr.
You're welcome. See you later.
Thank you.
You're welcome.
Thank you, Mr. Bohr.
You're welcome.